Okay, so I'm going to talk about MPI internals. Now, as I said, the MPI is a specification of function calls which do various defined things. How it's implemented is left to the library developers, but this is sort of a generic. These are sort of generic, features, things which are likely to be done. I can't speak to the actual details, but these are things which are commonly done and will allow you to understand how performance works. So I'll talk about a bit about the MPI library structure. I'll then talk mostly about point-to-point because that's the fundamental, and it's what a lot of things are built on, and that's what the exercise is based on. I'll talk about collectors and groups, communicators, and single-sided, but really the focus of this talk is on point-to-point. So we have until just check the timetable. Yeah. We have, so I aim to lecture for sort of 3/4 an hour and have at least 3/4 an hour for the practical. And I'll talk a bit about collectors, groups, and communicators and single-sided, but really point-to-point is the fundamental thing to understand, both in terms of how MPI works and also in terms of the exercise. So, any large piece of software is split into lots of packages, but there's actually a natural sort of decomposition for an MPI library following the chapter of the MPI standard, which at least used to be point-to-point collectives, groups and communicators, topologies, process creation, one-sided MPIO. There will be maybe more stuff there now, but that's sort of, at least for MPI 3, that was a standard sort of breakdown. There may be, obviously there may be hidden modules, internal modules. So I said there would obviously, if you downloaded an MPI library, there will be other modules, lower level stuff. And I said if it was MPI 6, there would be this ADI level encapsulating the network access. So point-to-point is the core of most MPI implementations. Collectives are usually, but not always, built from point-to-point. As I said, if you standard MPI library, a portable one will have collectives such as all, reduce, gather, scatter, broadcast, implemented using an efficient algorithm, but fundamentally calling point-to-point calls. That isn't necessarily true, but again, it's not useful to understand that. Someone actually asked about I/O in the break. Within MPI, there is the MPI I/O standard. I don't cover it here. It's covered in a separate course. But again, MPIO, there is an implementation of MPI called ROM-IO, which actually just requires basic MPI. So most, if you download an MPI implementation, if it's compliant, it will have MPIO in it, but they're probably using the ROM-IO library, which just calls basic MPIO. There's a lot of point-to-point calls, but probably at the lowest level, these are all built from a simpler set. So fundamentally, there will be a set of functions in some very low level set of functions, as I said, to send n bytes of data from process A to process B, and you can build everything else on top of that. So I'm going to sort of talk about, we're going to talk about point-to-point performance. How are we going to characterize point-to-point performance? And what we're going to measure is we're going to measure the time it takes to send a message between two processes. But we're going to have a model for that. And my analogy, I think it's useful, is a car journey. So, let's think about not how long does it take to send a message between two processes, but how long does it take me to drive to some location. So my car is parked near my garage, and it's 5 minutes to walk there. And after that, my average is 60 kilometers per hour when driving. How long does the journey take? What is my average speed? Okay, so for example, you will see that the time to do a journey as a function of the distance is linear, because of course I'm driving at constant speed. So the longer I go, the longer it takes, the further I. Well, there's a non-zero intercept because it always takes me 5 minutes to do anything. So there's a 5 minute, turn out to be what we would call latency in terms of message passing. There's an overhead of 5 minutes, regardless of how far I drive. But after that, then the time increases linearly. When we do tests like this on computers when we're ping-ponging a message, we tend to go up in factors of 2, 1, 2, 4, 8, 16, 32 bytes. So the standard thing is to plot this on a log plot, so the time against the distance in a log. And on this, what you see is it doesn't look linear. But because of this intercept, what you see is a fairly constant time up till about 5 or 10 kilometers, and then what looks like a very rapid rise. It's linear, but it's important. This is how we would typically plot things in reality. So this is but this is a simple finite time for any journey plus fixed speed. So the small and large distance behavior are very different, okay? Because small distances, if I want to travel a small distance, it takes a constant time of 5 minutes. Yeah, anything up to about a couple of kilometers takes me 5 minutes, because the time taken to travel that small distance is dominated by the 5 minutes walk to the garage. Okay. However, the long distance behavior achieves a constant speed. Okay, so if I look at the time for for short distances, the obvious thing to plot is the time it takes me, and you'll see that's constant 5 minutes up to a few kilometers. Then it starts to rise. If I plot my average speed, okay, long distance achieve a constant speed of 60 kilometers per hour. So small journeys are constant time. Large journeys translate into constant speed. But where's the crossover between small and large? Well, the obvious parameter here is n.5, and we'll see. Well, this I am going on to talk about message passing later on. What journey takes an equal time to drive as walk? Okay, so n.5, if I take the speed times my walking time, okay, that's 5 kilometers. So what n.5 is the driving speed times the time it takes me to get to the garage is 5 kilometers. This is saying if I travel 5 kilometers, I spend as much time walking, exactly the same amount of time walking to the garage as I do driving. And that turns out to be the crossover point between what you would call the small distance behavior, which is constant time, okay, and the large distance behavior, which is constant speed. Okay, so the important so we've got 3 parameters here. We've got the overhead, which will turn out in network parameters to be the latency, which is the overhead regardless of how far I travel. We have the asymptotic speed, which will turn out in network terms to be the bandwidth in gigabytes per second. But an important parameter is the crossover point, the n.5 between the small and large distance, or for network small and large message behavior, which is n.5, and that turns to be 5 kilometers. So it's basically saying if I'm traveling less than 5 kilometers, it's not really worth driving. So for point-to-point MPI, the latency is the overhead of sending any message. It's the time to get a short message onto the network, and typically on a good network that would be around about a microsecond. Okay, so you have to be careful here. In message passing terms, latency is the overhead of sending any message. Computer science people would actually probably talk about the latency as being the total time. That's not, latency is the time, the overhead, the time to send a very short message. Okay. The bandwidth is the rate of transfer on the network. It's the network bandwidth, which on a modern network could be something like 10 gigabytes per second. And these we'll see what these parameters are on ARCHER2, and you can work them out on any cluster by doing a simple message operation. But for example, here, if we take standard parameters, where the latency of getting any message on the network is about a microsecond, which sounds like a very short amount of time, but remember, modern processors are clocking at gigahertz, so that's many thousands of cycles. The bandwidth, the rate of travel on the network, maybe 10 gigabytes per second. Here, n.5 is 10 gigabytes times 1 microsecond, which is 10 kilobytes. So for these standard parameters, when I say short message, a short message is one where the time to transfer the message is dominated by the startup, by the overhead, and that's round about 10 kilobytes. And the above that, we start to be looking into the finite. We're saturating the network. So if we plot the time against the message size, you'll see that at n.5 it starts to take off. And if we plot the the bandwidth in gigabytes per second across against the message size, we'll see above 10K, we start to get asymptotically flat bandwidth. So N.5 is important. So whenever you say small and large message, you mean this crossover point, and it's basically the latency times the bandwidth, which gives you this crossover point. So how does this translate into MPI? Well, we've seen MPI communications mode. MPI defines multiple types of send. There's buffered send. So the buffered send complete locally whether or not matching receiver has been posted. That means it is the MPI B send returns always unless it runs out of buffer space. And the data is buffered somewhere until the receiver is posted. In practice, it's probably buffered locally, but you don't really know, but that's the model. And as we saw in the quiz, buffered sends fail if insufficient buffering space is available or attached, as we said. Synchronous sends can only complete when the matching receiver has been posted. It's like making a phone call. And the problem about buffered send is you might run out of buffered space and your send fails. The problem with synchronous send is there's an overhead, and also if you don't post a matching receive, then your program will deadlock. So there's also the ready send. You should never use this, but I mentioned it just because it's the standard. Ready sends require the receive to have been posted, and it's up for you to ensure this. And this is madness. It's only there for historical reasons. There must have been a message passing library pre-MPI that had this concept of ready send, which is saying I want to send a message and I guarantee the receive has already been posted. You can see if you know that, you can clearly apply some optimizations, but it's crazy. You should never do that. Okay, so I only mentioned it to tell you should never do it. So standard send is the one which is which we hopefully touched on the intricacies of it in the quiz. Standard sends may be either buffered or synchronous depending on the availability of buffer space and which mode the MPI library considers to be the most efficient. So as I said, in practice, MPI will buffer for standard send. MPI will buffer small messages but not buffer large messages. Where's the crossover point? Well, you don't know, but we can find out. And typically it does tend to be around a few tens of kilobytes. Application programs should not assume buffering or take complete. So the biggest mistake that people make is they assume the MPI send, the standard send, is always buffered. It is not. And so as a programmer, you should always be defensive, and you should always assume that MPI standard send might be synchronous. So you should program as if MPI send is synchronous, but at runtime you may get the behavior of buffered send, in which case it will be faster than you were expected. So a few things about messaging semantics. MPI requires the following behavior, and an MPI library requires ordered messages. Okay, you may never have thought this, but messages sent between two endpoints are non-overtaking. Now, for synchronous send, this doesn't mean anything. It's like saying, if I make two phone calls, can they arrive in a different order? Well, they can't. You make one phone call, you put the phone down, you make another. However, if you send two emails, can they arrive out of order? Yes. There's no guarantee if you send two emails or post two letters, they will be received in the order they were sent. MPI does require that. No matter how you send messages, the order is preserved. And actually, that's actually quite a lot of work for the MPI library, because at the network level, messages are split into packets and they can overtake each other. They can go different routes. However, actually, most MPI programmers don't realize they assume this. If you didn't have ordering, it would be very hard to write correct programs. You could send a message, then send another message, which was saying, okay, you could have a message which is to say, I've finished. So you can send a message, you can send a data message, you can send a message saying I've finished. If the I've finished message overtook the data message, your program would go wrong. Fairness, MPI does not guarantee fairness. What I mean there, if you do an MPI receive from MPI any source, is it guaranteed that the sources will all be treated equivalently? No, it doesn't, but many implementations attempt to do this. Resource limitations, there should be a finite limit on the resources required to process each message. This is why MPI send cannot guarantee to buffer every message, because you could do an infinite number of MPI sends and eventually the MPI library would run out of space. So this is why MPI send cannot guarantee to be asynchronous, to be buffered. It can try, but at some point it says, look, I can't buffer because that would require too many resources. Progress, we'll come back to this, but outstanding communication should be progress where possible. This means that, so we'll come back to this. Basically, you might think that you might have a model where you think that MPI has some thread in the background keeping things going. That's not true. So we'll come back to that. But this is the way that MPI operates is that maybe slightly different from your mental model of it, and what that's to do with progress. For example, if I issue a non-blocking send or even a buffered send, okay, the routine returns to me before the message has been delivered. When and how is that message delivered? Well, MPI is required to keep progressing things, keep things ticking over in the background, but how it does that may not be how you think it does that, and I'll come back to that later. So here's message progression, actually. So for example, if I'm rank equals 1, I specify a non-blocking receive, okay? So I've posted a receive, okay? If I'm rank 0, I then do synchronous send to rank 1, okay? Then we have, this is a very, very, very contrived program. Then we have a barrier, okay? So imagine, okay, so rank 0 will only reach the barrier if its send to rank 1 is completed, okay? So imagine that imagine rank 1 is running ahead. Rank 1 posts the MPI receive. It says I've set up an I receive, okay? So there's a receive waiting in the background, ready to get this incoming message from rank 0. Then rank 1 goes to the barrier, okay? So imagine rank 1 just sits in the barrier, doing nothing but waiting for the barrier. Rank 0 is now trying to send to rank 1, okay? But rank 1 is sitting in the barrier, and so it won't receive the message. The point is, you may think that when you call a barrier, you just sit there in the barrier. No, what MPI actually does is, rank 1 calls the barrier, so the MPI goes, okay, rank 1 is supposed to be in the barrier, but what I will do is, I won't just sit here doing nothing. While I'm here, I will keep things progressing. I will monitor outgoing sends and receives. And in this case, it has to keep ticking over, keep polling that outstanding I receive, so that it can receive the message from rank 0 when it comes in. Okay, so what MPI, so you may have a mental model that MPI is running continuously in the background. It isn't. In most cases, the only chance MPI has to do anything is when you call the MPI library. So what MPI does is that it effectively, every time you call an MPI routine, before it does anything, it uses it like a manual interrupt. It says, okay, David wants me to do something, send a message, but before I do that, I will go away and check if there's anything going on in the background. Like, oh, right, there's an outgoing message that it keeps things ticking over. It keeps the MPI library, the queues progressing. And that's, so MPI, when you ask MPI to do anything, the first thing it does is probably go off and do other stuff, bookkeeping stuff, before it does what you want it to do. You might think there's multiple threading. You might think, why doesn't MPI have a thread which ticks over in the background, keeping things progressing? Well, that's problematic, and we'll talk about that when we talk about hybrid MPI OpenMP. MPI defines both blocking and non-blocking calls. A blocking call waits until the message is sent. So blocking MPI send will wait until the message has been delivered till it returns. Because that can result in deadlock, MPI gives these non-blocking calls where you say, please start this message operation, give me a ticket back, your request, and you wait on it later. So most implementations will implement, but however, at the very lowest level, most network protocols are non-blocking. So actually, most implementations will focus on doing non-blocking operations, and blocking messages are actually a special case of that. And so if I ask MPI to do synchronous send in a blocking, you might think it just sits there making a phone call, waiting for the receive to happen. It doesn't do that. What it does is it goes away and it basically every now and again checks, but keeps things progressing in the background. So while the application may be blocked, the MPI call won't return control to you because the synchronous send hasn't been received. Internally, it is ticking over. So in fact, blocking calls which you call from your application internally probably map onto a non-blocking send, receive, and await. But that's sort of a slightly technical issue. So here we have a point-to-point example. You know, the way we would want to do point-to-point send and receive is you might do an MPI I-receive. So we want to do a halo swap. We want to do a boundary swap. So you post an I-receive from our up neighbor and an I-receive from our down neighbor. Okay, so they are there. They are then waiting. Okay. I then do a synchronous send to my down neighbor and a synchronous send to my up neighbor. When I call this synchronous send, okay, it doesn't sit there and what it will do is it will keep polling. It will keep polling and processing the potential incoming messages from other people before it does it. So these MPI send, this program might deadlock if MPI send did nothing but try and do the send. What it actually does is it looks at whether it can do the send, but at the same time it's polling to process these outstanding I receives, and then you can do a wait. So if you think so, that's so, and also this code, this code has a potential problem if your up neighbor and your down neighbor are the same. You know, so the issue here is imagine where I have periodic boundary conditions. So you know, the up of, and I'm running on 100 processes, the up of rank 98 is 99, the up of rank 99 is back to rank 0 again. Okay. On a small number of processes like 2, there's an ambiguity because rank 1's up neighbor is 0 and its down neighbor is 0. Okay, so this I receive is an I receive. These two I receives are from the same neighbor. Okay, so when I do this send, okay, it will match both of these I receives, but I want it to match this one. Okay, the send down should match the receive up. That is guaranteed to be correct here because of message order preservation. These messages will be received in the order they were sent, so it's guaranteed that that send down matches that receive up. It's something of a technicality, but when you do halo swapping, you shouldn't do receive up, receive down, send up, send down. You should do receive up, receive down, send up, because in some cases there can be an ambiguity. The up and the down neighbor can be the same. You're sending and receiving to the same neighbor, to the same rank. How do you make sure that the right send match the right receive? Well, you can do tagging, but the elegant thing is to do message order preservation. So that's just a slight aside there. Something you may not have come across is persistent. MPI defines persistent communications. They're like non-blocking, they can be run multiple times. The rationale here is when you do a send and a receive, you might do 1 million sends for halo swapping. Every time you call that send, it's the same buffer, the same data type, the same count, the same everything. Okay. So what you can tell MPI is you can say, look, I am going to do this send or this receive, this message passing operation many times. And the advantage there is the MPI can analyze, do error checking and analyze the parameters once and only once. So at the low level, they're mapped onto the same set of calls as blocking, non-blocking. Now, it turns out that for point-to-point communications, there's very little that MPI can do. There's very little advantage to this persistence. However, for collectives, there's a lot because when there are potentially a huge number of possible algorithms to implement a collective operation. Which is the most efficient algorithm will depend on how big your buffers are, what your data types are, how many processes you're doing. And so this persistence is actually much more useful for collectives, which is now, but they were originally implemented only for point-to-point. So they're not particularly useful, but the way it works is the MPI, you have an MPI receive a NIT, okay? So rather than doing the MPI receive, you say, and you pass all the same parameters as you would to an MPI receive, but you're telling MPI, sometime in the future, I'm going to call an MPI receive with these parameters, okay? sorry, my cursor's got, with these parameters. And you get back a request which identifies that operator. So it registers this with it. Sometime in the future, I'm going to want to do this receive with these parameters, this receive with these parameters, this send with these parameters, this send with these parameters. And then later on, you say MPI start all. I want to now kick these off. I want to do all these off. I want to do two receives and two sends. And then you do a wait all for them to complete. The only subtlety is that MPI does not guarantee these are started in any particular order. So to get message matching working in this case, you have to be careful and you'd have to use tags. You'd have to tag the messages appropriately. So yeah, so persistent communications are there. MPI does include a lot of derived data types. Under the hood, MPI probably just uses them as a pack-unpack instruction. So I'm not going to, but so derived data types are a very elegant way. So for example, if you're sending Halo data, which is often non-contiguous in a multi-dimension, you can pack the Halo data, send it and unpack it. It's much more elegant to use a derived data type. There are derived data types which map onto non-contiguous subsections of data. You might pay a cost here, but you know, at some fundamental level, MPI is probably doing the pack-unpack for you. But I would recommend using derived data types because they're much more elegant. However, you have to realize that under the hood, MPI may just be doing a pack-unpack. So the most important part of this lecture, I think, is now the protocols. How is a send and receive message? How is a send and receive implemented? So obviously, MPI is message passing. Somewhere you need a way of delivering packets of data messages to a remote process. But when you send a message, MPI may send, it's going to send your data, but these may correspond to the user or protocol messages. So MPI will have some protocol, some mechanism for sending and receiving data. And so the model you have is whenever a process sends an MPI message, it will send an initial protocol message must be sent, which might just be the envelope base. So what you're going to do, your model, if I start, I want to send a message to somebody, what I will do is I will send a little header saying, I've got a message for you, and it is 100 integers, okay? I want to send it to you in the future. We'll see that there are variants on this, but that should be, you know, initially when you send a message, you'll just send a little header saying, there's a message waiting for you, come back and get it when you want it. So minimally, it will contain the envelope information, you know, where the data is coming from, what it is, and where it's going. And most implementations use a fixed size header for all messages. So, you know, it might be 128 or 256 bytes or something. So your mental model should be there is a header message, a metadata, a protocol message, which is sent whenever you issue a send. The receivers will have some message queue. So when you issue a receive, so we posted in tweets, so a receiver will have a list of outstanding, a process will have a list of outstanding receives, okay? So imagine that you notice there's a little protocol message coming, said somebody wants to send me some data, okay? If you've already issued a receive for that, you can match it and process it. So if the receiving process has already issued a matching receive, the message could be processed immediately. If not, you're saying, well, this guy wants to send me a message, I must be issuing a receive later on, but I'll park it for the moment. So this is called a foreign send queue. So you'll have a queue, have a list of all the receives you've posted, but also a list of all the incoming messages which you haven't been able to process yet. And that's called a foreign send queue. It's foreign because it's come from somebody you didn't expect. Yeah. Also, when you issue a receive, the first thing you do is, right, I want to do a receive. Has somebody already sent the message? So you look in your outstanding receive queue. If not, it has to be added to the receive queue. So your model is that every process has a list of outstanding sends and receives which haven't yet processed. Now, there could be lots and lots of queues, but in practice, most MPI implementations have a single queue for all the outstanding sends and all the outstanding receives, which have not yet been resolved. Okay. And that can mean that issuing a receive can be quite heavy overhead because it has to look first through all the outstanding incoming sends it hasn't processed before it goes out, or if you issue a send, it might look through the outstanding receives. So typically MPI implementation use two different underlying protocols. Okay, these are eager and rendezvous, and there's lots of variants on these basic protocols, and we will see when we do the exercise, we can see the implications of these in practice. But the most obvious one is the eager protocol is an optimization. Okay, so what so I said that when I want to send somebody a message, I will typically send a little header message saying, here's the data. Okay, sorry, I want to send you some data, come back to me later. If the message is small enough, actually what MPI will do is it will actually send all the data at the same time. It will say, I want to send you some data, and actually here it is. Okay, that's called eager because the sending process eagerly transfers the data immediately. Now clearly that means there must be some space on the receiver. So this can only be done for moderate sized messages, but below some threshold, we can see what that threshold is experimentally. MPI has an optimization where it sends all the data straight away. Okay, so if there's no matching receive, it has to be buffered, obviously. Okay, and that means there's a limit on how often you can do this. But that means that eager, buffered and standard sends can complete as soon as the initial protocol message has been sent. So if you do a standard send or a buffered send, okay, where you don't require acknowledgement of receipt, what you do is you can just say, okay, MPI says David wants to do a buffered send or a small standard send. Okay, it's a small message, so I can just chuck that straight over to the receiver. There's some space there to receive it, and then I can just carry on. Okay. For synchronous send, it can do that. Okay. However, synchronous send requires that you wait until the message is until the receiver has been posted. So when the receiver is posted over here, there will be a protocol message come back. But eager protocol is that MPI has optimizations for small messages where, and we'll see it's around about 10 kilobytes typically, where it will immediately send the data over without waiting for acknowledgement. However, obviously this eager protocol requires it to be buffering the receive process, and it means there's a limit on how large or what size of message you can do. I'm not going to talk about ready messages here. So typically, if you call MPI standard send, okay, what it will do is it will say, is this message small enough for the eager protocol? If it is, it will do buffered, and it will basically send the message straight away and return. If it's not, it will do synchronous, and that's where the threshold comes in. Okay, so the rendezvous protocol is basically for large messages. Okay, for a rendezvous protocol, the initial protocol must only contains the envelope information. So you say, okay, I want to send you some data, come back to me later. Later on, a receive will be issued, and then the sender will get back to you, and then you can send. So the eager protocol is a one-way thing. You ask to send a message, it's small enough that you can just send it straight over and carry on. If the message is large, you send a header over. At some point, the receiver gets back to you, and then you send the data. So there's 3 transactions: notification that you want to send a message, a handshake that it's been received, then you send the data. Okay, and so in this sense, send acts as a synchronous send. It waits for the matching receive. And so the reason that we have this optimization for eager for small messages is that this I want to send you a message, handshake, I'm ready, then send the data, has this 3-way transaction, which is quite a lot of overhead. Actually, for very large messages, this can actually help, because you can bypass some copying, but typically the rendezvous protocol it introduces an overhead compared to eager. So typically what this means is that MPI performance, you will see a threshold. So that for small size messages, you will get a particular increase of time with message size. Then you will see a sudden increase when MPI says, okay, the message is too big now to do an eager protocol. I have to now switch to a rendezvous protocol, and you'll suddenly see an increase in latency, and then another increase as you. So typically, this is the kind of this represents a protocol switch. There's an optimization for small messages where it uses the eager protocol, where which minimizes the handshaking. But for large messages, it uses this rendezvous protocol, there, back, and there again. There is actually another protocol variant for very short. I said that the header message was typically of a fixed size, say 128 bytes. If you're just sending a single byte, a single integer, it can actually fit that on the protocol. It can send a little protocol message of a fixed size and actually say, look, the data is actually in the message. This is an optimization for. So this is a bit like sending a postcard rather than an envelope, rather than a letter. If you're sending a letter, you write your letter on lots of pages, you put it in an envelope and write the envelope information on the envelope. A postcard is there for short messages. The envelope contains the data. Okay, so again, not only will you see a large data region, a large message regime, and then a switch to eager, you may even see another switch down here, but for very small messages, it's even faster because the data is so small it can be fitted on the header packet. So it's effectively sent for free. Short message is a variant of the eager protocol, but basically the message is so short that you can actually fit it into the header. So you send the message for free. Some interconnects, some transport networks allow DMA, direct memory access, direct memory copy across the network, and this could mean that for very, very, very large messages, you can get increased bandwidth because there's no copying. However, this typically comes in at really, really large message sizes of tens, hundreds of megabytes, and we typically don't see it. So again, in principle, there could be 4 regions. Okay, the very short message region, where there's an optimization where the data is put on the protocol header, the eager region where the data is sent without a rendezvous approach, without a handshaking. Then you go into an intermediate message size where there's a handshaking overhead, and for very, very large messages, the library may actually use this direct memory to memory copy, but that requires a lot of overhead, a lot of synchronization, and that has a heavy effect on the latency. I thought I had a. So that's a very good question. So that's a very good DM. So DMA. So it does. So DMA. What I mean by DMA is the ability to send data between directly over the network. You're right. So if you're sending messages between processes on the same node, as you say, right? Then it will do. So but you're right. It will do a direct memory copy. Yeah. So for example, the header information might actually just say, I want to send you some data, and here's the address of the data, and then it can just copy it directly. So you're right. There is so I should have mentioned this actually. That for on-node messages, a lot of this can be done by shared memory copying. You're right. It's not quite what I mean by DMA. DMA means direct memory access across the network. You're absolutely right. With ranked on the same system, on the same node, you will get it will bypass a lot of this and do direct memory copying. Does that answer your question? Sorry, that's a very good point. And we will see this in the point-to-point exercise. You will see that the latency is a lot lower for messages between processes on the same node. Is that what you meant? Sorry, did I understand your question correctly? It's a good question. But yes, MPI implementation, yes, we'll recognize that. Collectives, again, I won't not. As I said, there's nothing in the library interface that says that collectives have to be built out of point-to-point messages. So, I mean, you hope that there are many possible ways of implementing collectives. A good implementation will build some kind of binary tree, and therefore the time taken to implement a collective will scale with a log of the number of processes, because the binary tree can reach, every step can reach twice as many processes, for example. But I'm not going to go into any detail. I think the only thing I want to say is that, you know, that if there is one optimization you should use for point-to-point MPI, it is do a small number of large data transfers rather than a large number of small ones to counteract the impact of latency. And for any MPI implementation, you should use collective algorithms wherever they exist, because they will be implemented efficiently. They may be implemented in some efficient point-to-point manner, but hopefully they map directly onto some hardware, onto some even more optimal. So, for example, to sort of follow up on Yannick's point, if you do a broadcast on a single node, then, for example, it might just do direct memory copies, because in principle, processes on the same node can access the same memory. It's a shared memory system. So MPI has the possibility of doing groups. Somebody already mentioned in the quiz that you would do subgroups. So logically, communicators are independent communication domains. In practice, the way that this is implemented is that there will be some. So when you send, so in practice, at the lowest level, MPI will send messages between different process IDs, where their ID is their native ID. It's their rank. It's their rank in MPI COM. Well, the important point about your rank in MPI COM world is it's globally unique. Okay, so if you're running on 1,000 processes, 0 to 99. However, you do in principle be able to need to distinguish if messages are in the correct communicator, and so actually hidden from you, not only will there will be some information on the header message saying this is for communicator X, and there will be some tag or a context on the message which says, by the way, this message is for communicator X, and so that allows you to. So fundamentally, at the lowest level, MPI is just sending messages between two processes. But the flexibility of being able to use different communicators and such like is implemented as like a hidden tag. Process topologies. Hopefully you've come across the fact that you can create topologies, things like MPI Cartesian topologies. In principle, this allows the MPI implementation to do clever placement of processes. Many don't do that. So using things like Cartesian communicators is an elegant way of programming, but doesn't necessarily give you performance benefits. However, where they come into their own is through collective neighborhood communications, and that's why I cover neighborhood collectives later on. Single-sided, again, I will cover this very briefly, but I'm not a fan of the single-sided applications. In principle, there is a way in MPI of allowing you to read from and write to another process's memory directly. An MPI puts it like a send without a receive. A get is like a receive without a send. The function calls are very, very complicated, in some cases complex and quite be ambiguous. And for many applications, the single-sided performs slower than point-to-point. However, where I think this concept of single-sided is useful is it allows you to do direct read and write to memory windows on a node. As I've mentioned before, allows you to have the concept of a shared array, a shared memory array, a la OpenMP in MPI, and I will cover that. So summary, there are many ways of specifying MPI communication. You know, what's fastest, people ask. Well, often, you know, it depends on the library, the hardware, the options. So performance portability is therefore hard. What may be the best way of sending a message on one system may not be the best on another. So I would say implement lots of methods, test them all and pick the best one. And I have a benchmark which will do that. But the exercise now is to actually just do a very simple point-to-point message passing operation and see if we can pick out these protocol switches which I've talked about. And so I will share the I go to, I don't normally like to do this. What I will do is I'll share my, give me a second. So I'm just having some problems with, okay, so I'm, hopefully you can see my entire screen. It's a bit difficult for me to, apologies. Yes, you can. Unfortunately, you get this strange, going to, what I want to say is, right. So if you go to the first exercise, day one, is the ping pong exercise sheet. There's an exercise sheet and some code. There are Slurm scripts which we use the short queue, but actually I have a reserved queue for today. So if you want to use a reserved queue, which I'd recommend, I would recommend. So there's a mistake here. So apologies. 668. That should be 86. So apologies. That should be both of these should be 863. I will fix that. Apologies for that. Give me a second. Apologies about that. I fixed that now. So okay. So there's an exercise sheet which goes through the exercise. There's a bunch of things to, but it does produce graphs and such like. So I mean, what I hope people will do is to basically run the code. If you download it, run it. It should so that this is the wrong. We're TA161 this time. Is to download it and run it, and you should be able to get a simple graph of communications which plot the time and the bandwidth. So we can maybe just run this, and having run out the box, there's a bunch of experiments you can do, which are ways of communicate of altering the process placement. Okay, but by default, the code runs two processes on the same node. So it's not particularly interesting for a real program, but basically it will at least give you a clean graph. So I'll just check that. Whoops. What I will do is run through. So we've got this. Our project is. Uh, 161, apologies, 161, sorry. So you will have your own, you will have this TOTP code 7611172. Sorry, I'm having trouble with that. Okay, I've got the wrong one here, so I need to do it. Uh, 827114. You'll have your own. Okay. I need to do /work /TA161 /TA161, and then your username TA161 DSH. and then I need to do this wget this code. I need to unpack it. Go to ping pong. I should be able to make it. And I should be able to the ARCHER2.job. It's pending, and now it's running. Get that output file, which has all the numbers, but actually the graphs are much nicer. Now, actually, I didn't enable. I'm going to have to log out and log back in again because I didn't enable graphics for this. So I'm going to have to basically. I won't be able to do the plot. If I go to persist plot time. So hopefully you can see that there is a the graph here, and it's quite hard to understand. There are two features of this graph. First of all, the initial this is probably wrong. The initial ping pong has some overhead, and I think that the time at 0 bytes is probably not accurate. The reason why this graph is quite hard to understand, so you can see that we do see this sort of constant time and then constant bandwidth regimes. But the reason that this graph is quite difficult to understand is this is, as I think Yannick pointed out, this is on a single node. Okay, this is doing a ping pong between two processes on the same node, and it's doing lots of tricks, which mean don't really know what the library is doing. It's actually when you do a message passing between nodes that it becomes maybe more interesting. And so the experiments are I've got written down here. You could try two programs on the same node. Yeah. So, but you want to maybe look at doing communication between different nodes. Yeah. So I would say between yeah. So I think also that you want to do communication between two processes on the on different nodes. So this is just just give you time to play around with this, and yeah. So if you look at the Slurm script, which is here. You'll see that this has one node and 2 tasks per node. I could do 2 nodes and 1 task per node, and that would immediately send a ping pong across the network. Okay, so that would then give me a different plot, and this should correspond, hopefully, be more like the behavior I described in the lectures, which will be correspond to different regimes of these sort of very small message, eager and rendezvous sections. Sorry, I'm now having a problem here. Let's do, yeah. So it's run. So this is okay. So this is the graph between message passing speed between two different processes on the on different nodes, and this you can see that there are a number of distinct regimes. Okay, so above a certain size, which is round about here. Okay, so I've got, so this is the time taken to send a message between two processes using the two protocols, standard send and synchronous send. Okay, at a certain point here, it is standard send and synchronous send become the same. So this is telling you that standard sending is becoming synchronous. So you would expect that below this point, then there is some optimization to do with the eager protocol. And it's happening at a very large message size. So I said that the eager protocol was normally at maybe 10 kilobytes. On ARCHER2, it's more like 100 kilobytes or more, and that is because it's a very large. You would not normally expect the eager protocol to be used up until such a large message size, but it is on ARCHER2 because of the way that on ARCHER2, large messages are split into lots of small messages, which can also be sent in the eager protocol. But so above the eager limit, which is very large value on ARCHER2, standard send and synchronous send have equal performance. Below the eager limit, synchronous send uses a rendezvous protocol, whereas standard send uses an eager protocol. And so the time for the standard send is less than the time for the synchronous send. Okay, so this is our eager limit. And then there are some glitches here, but for very small messages, which is below 128 bytes, we get this is very small message where presumably the data is sent along with the protocol message. So by doing a ping pong between processes on different nodes, you can recognize these three regimes: very small message, which has a very low latency; intermediate message size, where still standard send is faster than synchronous send because standard send uses the eager protocol, but synchronous send still has to do this handshaking, this extra rendezvous protocol, and above the eager limit, where standard send and synchronous send become identical. So that's sort of the kind of behavior which you might expect. So I don't know. So I mean, maybe let people play around with that. And we can, what I'll do is, I'll stop sharing for a moment. So I don't know if anyone has managed to run that example, but it should run out the box like that. If you get slow turnaround in the message queues, sorry, in the Slurm queues, you'll see that you can put down that reservation, but it looks like the short queue is running quite nicely for us today. So we'll do, have a go at the exercise and to discuss. So just take a, if anyone's having any problems with logging in, then please, if contact me now, and we can sort them out. Logging into ARCHER2 can be slightly quirky, so that does have its issues, but I'll be around. So another thing I should have pointed out here actually is that I've gone through that rather quickly, so I will basically go through in a bit more detail. I was rather rushing there, apologies. If you look at the output for the first one, so the location of the process is controlled by your Slurm script, but the program does print out where things run. So by default, it says rank 0 running on core 0 of node this. You can see here that the two processes were on the same node. Okay, that's why I'm printing this information out, because that was the default configuration. But I said that the next one had a different configuration. Let's see if that's true. Yes. Rank 0 running on core 0 of node 2354, rank running on core 0 of node 2405. So here they were using different nodes, and therefore, okay. So I think, Theo. Okay, so I'd like it. So let's do a breakout session. I think I know what's happened here. So Theo, that it could be. You may have -x. There is an issue that GNU plot is a very, very old program. Yeah, I haven't splot. So I'm assuming some kind of default term. Yes, there can be issues here. Are you on a? Sorry, who was it? Theo, are you on a Mac? What's your? Let's think. If I could just. What's dollar? If you echo dollar term on your ARCHER2 window, what do you get? Oh, okay, so that can't be it. Okay, that's what I would guess. The other thing is to copy the files back locally and do the GNU plot locally. So yeah, I've seen this before. I'm surprised it happened with Ubuntu, but it'll be some terminal setting which is confusing GNU plot. Maybe it's your local. What do you get locally? What do you get for echo dollar term in your local terminal, not the one on okay. Do you get X725 color for the local terminal? Yeah, so I think you may have to copy them back. I have seen this issue before, but I'm afraid it's a bit difficult. Yeah, okay. So I think it was Adeleki. Adeleki, can we go into a breakout session? I think we can sort this out. Is that okay? So be with a sec. Okay, so just before, I think it might be worth. I've got a few sample results here, which I think might be worth looking at, and then we can just maybe discuss them. So I'm just going to check. I've just done the two very, very simple ones, which is 2 processes on the same node and 2 processes on different nodes. So I'll go. I'm just looking for the. I need to share my screen. Sorry, apologies. So do is hopefully people can see. Yeah. So can people just can someone say? Can people see those 2 plots? Yeah. Sorry, I'm trying not to. Yes, great. Okay, fine. I get this problem. So we saw this before, and so we can see here that this is on a node. So this is actually using lots of shared memory tricks, for example, however, you can see that in this case, standard send is always quicker than synchronous send. So this model we have, protocol message, maybe doesn't work at all. Maybe it does something completely different on a node. Now, the reason why I'm being a bit throwaway about this is if you're running a very large application on tens, hundreds of nodes, the message passing performance within a node doesn't really matter. It's fast, it's not your limiting factor. The limiting factor of the speed of your code will be the message passing between nodes. So it's really the message passing between nodes, which is the speed of the network, which is really important for real applications. But it's just interesting to look at this. And you can see here, the standard send is always quicker than the synchronous send. And there's a bit of variation. But the main point here is I want to get these numbers here. This is 1 point, it's 10 to the minus 1, 2, 3, 4, 5, 6. That looks to me like a microsecond. Yeah, that's 1 microsecond. 1, 2, 3, 4, 5 ones. Yeah. So the latency on a node is about a microsecond, a millionth of a second, which is quite fast. The bandwidth is topping out at about this is gigabytes per second. Megabytes per second at about 10 or 10, 11 gigabytes per second. That is just maxing out the memory bandwidth on a node. Okay, so but I think the reason that we don't see this clean, various thresholds is that it's doing something completely different on the node. This has been optimized. So these are interesting. They give you figures that you get 1 microsecond latency and about maybe 10 or 20 gigabytes per second bandwidth, but that's not particularly important for large-scale applications. What we're interested in is between nodes. So let's look at those ones which we've seen before, and here we'll see that we saw this very clean above the eager limit. Send and standard send and send become identical. The intermediate region where there's this eager optimization, where standard send is faster than synchronous send, and then in the where we also see this drop for very small messages, which is kind of the 100 odd bytes message, where we get very fast performance. For the bandwidth, we're seeing that the bandwidth we're getting is about 10 gigabytes per second, the maximum we're getting. Now, I think it's important to recognize that this is like the miles per gallon figure that your manufacturer quotes you. This is a never to be exceeded figure. And the reason why this is a slightly fake figure is that, the reason it's a slightly fake figure or unrealistic figure is that, remember, here we have one process on each node sending data across the network. In reality, in a real program, you'd have 128 processes on each node sending data, and so there'd be a lot of congestion. All these nodes, all these processes on the same node are sharing the same network. However, I have a more realistic benchmark this afternoon, which actually does a 3D halo swap. But I think, and I went to the latency. You'll see the latency here is that's a microsecond. Yeah, so it's 1, 2, 3, 4. It's about 5 microseconds latency. So the latency is in the handful of microseconds. So it takes 5 or 10 microseconds to send any message at all, and for a very large message you get about 10 gigabytes per second. And yeah, so hopefully those are interesting figures. But I think that they're the kind of figures you should keep in the back of your mind, that latencies are of the order of a few microseconds at best conditions, and there we saw that the bandwidth was maybe about 10 gigabytes per second, which is pretty good, and that shows it's a fairly good network. I'll stop sharing. Sorry, I hit the share screen thing. So what we'll do is we'll have a lunch break now. Come back at 2. What I'm going to talk about at 2 o'clock is how the way that MPI implements point-to-point affects what the most efficient way of doing message passing. I think the problems you can have, things which slow down your code, and also ways to improve that. And then we'll run another simple benchmark, but which will hopefully show in practice, what the best way, or at least on ARCHER2, of doing a halo swapping is. And I'll finish the day with a final lecture on neighbourhood collectors. Okay, so hopefully see you again at. Sorry, I'm playing with too many windows here, as I always do. See you again at 2 p.m. Enjoy your lunch.